Hello, in this video we will be looking at definite integrals and the fundamental theorem of calculus. To begin, we want to define what a definite integral is, and I'm going to start with some background about Riemann sums. So let me begin by posing a question. Suppose that I have a function, it could be any function, but I'm going to pick x squared plus 1, and I'm interested in knowing the area underneath that curve from one x value to another one. I've graphed what this would look like over here on the right. We have the graph y is equal to x squared plus 1, and then I've shaded all of the area underneath the curve from the x value 0 to the x value 3. Now this, geometrically, this is not a standard shape. We have the left side is straight, the bottom side is straight, the right side is straight, but the top edge of this is some kind of a curved shape, so we can't use the formula for a rectangle or a triangle or a circle to compute what all of this area is. The question is, how could we go about approximating the area, or really, how could we compute this area? But we're going to start by, first of all, approximating what that area is. Okay, the one shape that we're going to rely on heavily in this background information is we know how to compute area of rectangles. So, step one, we would think about breaking the area under the curve up into some number of rectangles. There's nothing special about 3 rectangles, but based on the fact that I started at 0 and ended at 3, I thought it would be natural to start with 3 rectangles. There would be a couple of questions we have to answer, like how does the rectangle correspond to the function? In this case, the top left corner of the rectangle is going to touch the function, is how I decided to make my rectangle. So I have one rectangle here, a second one here, and then a third one here. And if I compute the area for any of these rectangles, recall we know that the area of a rectangle is 1/2 base times height. Then what we would figure out is we have an area of 1 for the first rectangle, 2 for the second rectangle, and then 5 for that third rectangle. So then 1 plus 2 plus 5 would end up being 8, and I would see that the area of these 3 rectangles together is 8. The next question we would ask is this approximation a good approximation for the actual area of the rectangle, or sorry, the actual area under the curve that we were trying to approximate? What we see here is we have this large gap here, and then a larger gap here, and an even larger gap here of areas that are under the curve but just aren't covered by the rectangles. So I would say this approximation of 8 is a fairly bad approximation, and in fact, it's missing significant chunks of the data. So the true area is going to be some number larger than 8. Well, the follow-up question is, how could I make my approximation better? Well, the answer to that is use more rectangles. So instead of having the width of each rectangle be 1, I could pick the width of each rectangle to be something else. So what if I picked the width to be 1/2? Then we would have 1, 2, 3, 4, 5, 6 rectangles. N is equal to 6. And in a similar manner, I just make the top left corner of each rectangle touch the curve, and I haven't listed what the areas of each of these rectangles are, and I'm not going to do that, but if we add up all of these rectangles, we would find that our area is equal to 9.875. You can compare this shaded area with this shaded area. We see that as we have subdivided it into more rectangles, we are going to have a better approximation of what the actual area is, but there's still obvious missing pieces. We're missing a piece here, 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 and here. So this number is still going to underestimate the actual area that's under the curve. Well, there was nothing special about the number 3 or the number 6. If I wanted to increase the accuracy of my approximation, I could just increase the number of rectangles. You could double this again to 12, or triple it to get 36, or triple 12 to get 36, or just pick any arbitrarily large number you would like. So what happens when n is 100? What happens when n is 1,000? I haven't drawn diagrams for each of these situations, but you can imagine having 100 rectangles in here. It would be a lot to look at. But what you will observe, if you let the number of rectangles start increasing without bounds, so 12, 36, 100, 1,000, what is the pattern we see with the areas? We start out with 10.91, then we get to 11.63, 11.87, 11.99. The idea here is that all of these numbers, the areas, are approaching a certain value. So this is reminiscent of a limit. It in fact is a limit. The limit of these rectangles, if n approaches infinity, so just let n get arbitrarily large without bounds, so you could set n equal to 1,000,000 or 1,000,000,000 or 1,000,000,000 or just increasingly large numbers. What you will determine is that all of the areas just converge to a single number, and we actually don't have to go much larger than 1,000 to see what they are converging to. It appears, just based on a visual inspection, that the areas seem to be approaching the number 12. So let's go ahead and write that in. Now, this is not at all a proof that this has happened, right? We can't prove that the limit would be 12 just based on computing a couple of examples, but this would give us a good indication, a good intuition as to what the area would be. So this background, all of this process of subdividing an area into rectangles and then increasing the number of rectangles would be called a Riemann sum. And specifically, if I'm putting the top left corner of the rectangle on the graph, we would call a left-handed Riemann sum. Now, in some calculus classes, you would spend a lot of time talking about Riemann sums. In a brief calculus class, this is the only part where I'm going to talk about them. From here, just to give you, we only do this to give you a background of the next definition. So what is the definition of a definite integral? You have seen integral notation already, so we have seen indefinite integrals that don't have the b or the a of a function, but when we include these two numbers, b and a, which we would call limits of integration, what we mean, the way this is defined, it's defined to be the thing we were just talking about. Now, this notation looks very intense, but we can break it down. This summation symbol, the capital sigma, just means we're going to add a bunch of things together, and what we're going to add are rectangles. So this doesn't look like a rectangle maybe to you, but the f is going to represent the height of the rectangle. This delta x is going to represent the width of the rectangle. So you have a width times a height, that's the area of a rectangle, and we are going to add up all of the areas of rectangles for n. What is n? N is the number of rectangles, and we want to consider what is the limit as the number of rectangles approaches infinity. Now, the implication here is that when you allow the number of rectangles to approach infinity, the width of your rectangles would start to approach 0. Now, as a technicality, in a Riemann sum, you don't require that the widths are all equal. So in the examples that you saw up here, the widths of my first rectangles were all equal to 1. In the second set of rectangles, the widths were all equal to 1/2. They don't have to be uniform, but when you consider the limit, they do have to be all approaching 0. Okay, again, that's kind of just a technicality, and in a brief calculus class, we're really not going to get into looking at Riemann sums much at all. So when this limit exists, we would say that f is integrable on the interval a to b. Now, that's really a lot of math jargon up until this point. Let's go ahead and look at what this would look like kind of practically in a couple of examples. The first thing I want to look at is how it relates to the area under a curve. So when you have a continuous function on an interval, if your function is greater than 0, so that means the function has to be above the x-axis. It's technically allowed to also equal the x-axis, but it should never go underneath the x-axis. As long as the function's above this x-axis, then the integral that we just defined is exactly equal to the value or the amount of the shaded area. So that's just based on how we have defined things. Now, when we defined this, we were kind of assuming that the function was above the x-axis. If the function happens to be below the x-axis, that would mean that the y values are less than or equal to 0 on the interval. Then what would happen is your definite integral that we just defined would end up being a negative number. So you can have negative values out of this definite integral, and the implication is that, yeah, you have some kind of area that's trapped below the x-axis. With that in mind, let's look at 3 graphs that each have a shaded area. And what I would like to do is just practice the notation, this definite integral notation, for each of the 3 graphs. So here on the left, what we have is we have a shaded area. If we wanted to write an integral that represents the shaded area, then first of all, we start with this integral symbol. We're going to have to decide what the limits of integration are. We're going to have to decide what the function is, and then we're going to end with a dx. So it's a definite integral with respect to x. The function is always just whatever the function is, whatever this line is, and that should be a given value in the example. So in this case, it's the integral of x with respect to x. Now, the next thing we would want to do is we would want to decide what are these limits of integration. So this bottom number here we call the lower limit of integration. This upper number here is the upper limit of integration. And these are x values. The lower limit of integration is the first x value that we encounter for our shaded region. So in this case, it would be 0, and then you scan over, and the upper limit of integration is this x value that's the largest, the farthest right, that corresponds to the shaded area. So we can put here our lower limit of integration was 0, our upper limit of integration was 1. Now, we will eventually in these notes talk about how do you compute this. There is a theorem, it's called the fundamental theorem of calculus, that allows you to compute a indefinite integral, so an antiderivative of x, and use these limits of integration to evaluate how much area was there. Now, for right now, though, what I want to emphasize is that this notation is the actual area that got trapped here. If the line is simple enough, like this is just a straight line, you know how to compute the area of a triangle. So the shaded area here is just a triangle. We know that area is equal to 1/2 base times height. So you could compute what is the base or the width of this area, or sorry, of the triangle, and then what is the height of the triangle. In both cases, we see it's 1. So the area, based on a geometrical approach, area would be 1/2 times 1 times 1. So we see that this integral is going to evaluate to 1/2. Okay, based purely on the fact that it means area under the curve of x from 0 to 1. Later on, we will have another way to compute this, especially for graphs like this middle one, where the shaded area is not a standard geometric shape that we have a nice formula for computing its area. Before we get to this middle one, though, let's go and look at this example on the right. So let me kind of divide my paper here into a couple areas for my work. So this integral on the right, this area on the right, if we wanted to write a definite integral for it, then we start with this integral symbol. We're going to have to write the upper and lower limits of integration, but I'm going to come back to those. After you write the limits of integration, you always write the function. So in this case, our function is x minus 2, and then you have to put in this dx notation. This dx is called a differential again, and all it does is it tells you that we are integrating with respect to x. So x is the variable that we see over here. All right, with that in mind, let's now put our limits of integration in, and then we will have notation that represents all of this area. Okay, so So what are my lower limit of integration and my upper limit of integration? Well, your lower limit of integration is the x value that corresponds to the start of the shaded area. We see that that's just 0. And then the upper limit of integration is the x value that corresponds to the last part of our shaded area, so that would be 2. All right, this thing here is an integral that corresponds to this area. When we evaluate it, again, you're going to have a technique to evaluate this just using calculus, using the fundamental theorem of calculus in a little bit. But since this is a nice geometrical shape, it's just a nice triangle here, we know that area is 1/2 base times height. In this case, our base is 2, our height is 2, so we find that the total area is 2. Now, we have to be careful with how we're saying this. The area, the physical area, is 2, but that's not what the integral will evaluate to be equal to. So this integral that corresponds to the shaded area evaluates to be -2 because all of the area that's indicated is trapped underneath the x-axis. All right, for this middle example, right now we can go ahead and we can write down an integral that is equal to this area, but we won't be able to evaluate it until we talk about the fundamental theorem of calculus. However, that doesn't stop us from writing the definite integral down. So in this case, we write a definite integral. The lower limit of integration is 0, the upper limit of integration is 1, and then the function in this case is x squared. We are doing this with respect to x. So I'm going to right now just write the notation. I'm going to say it's equal to something. I don't know what this value is. I have ideas about what this value might be, but I can't say for certain what it is. Looking at the graph, if I wanted to shade this in, we see here that 1 square unit would be this square right here. So I just shaded, or I just boxed in 1 square unit. So I know that this has to be a lot less than 1. And in fact, if we wanted to split the square in half, we could make this triangle. So this blue triangle now is 1/2 of a square unit. So whatever the answer ends up being, it's going to be much less than 1. In fact, it's going to be a little bit less than 1/2 of a square unit. So some number bigger than 0, but that's smaller than 1/2 is going to be our answer. Let's talk about what is this method. How can we compute this? What is the fundamental theorem of calculus? So the fundamental theorem of calculus says that if you have a continuous function on a closed interval, then the definite integral of the function will exist, and what it is equal to is it's equal to capital F of b minus capital F of a. What is capital F? Capital F is any function such that the derivative of capital F is equal to lowercase f. Another way of saying this, when we say that the derivative of capital F is equal to lowercase f, what we mean is we mean that capital F is an antiderivative of lowercase f. All right, so that is how we compute the area under a curve from a to b. You find an antiderivative of the original function, so that would be capital F. Once you've figured out this antiderivative, then you plug in the two endpoints, these two limits of integration, and then subtract them from each other. Of course, starting with b and then subtracting off capital F of a. Okay, now there is some notation that goes along with this. So when we evaluate this here, one way to write capital F of b minus capital F of a would be using this notation down here. It's equal to capital F of x evaluated at b minus a. So let me just write this in to make it clear that these are equivalent. And now let's go ahead and look at that example that we weren't able to compute the area of before. So what we have here is we have the definite integral 0 to 1 of x squared with respect to x. We need to figure out what that is. Let me give myself a little bit more room here. So what the fundamental theorem of calculus says is you would need to think of some capital F. We know that lowercase f is x squared, so I need to think of an antiderivative of x squared. Well, we have properties of antiderivatives. This would be, I guess, rules for computing antiderivatives. It would be x cubed over 3, or another way of saying that would be 1/3 x cubed. Now, technically, when you compute antiderivatives, there would be a constant of integration here at the end. So most times when you compute just a generic antiderivative, you have to include this plus c at the end of either of these two. However, in the fundamental theorem of calculus, this is going to be true for any value, like for any antiderivative, which means that you can pick plus c to be any number that you would like. So yes, the generic form of an antiderivative does have to include the constant of integration, but when you're applying it in the fundamental theorem of calculus, you are allowed to pick plus c to be plus 0. So I will stop showing the plus c just with the implication that I'm choosing it to be 0. All right, now that we've figured out what capital F is, we need to figure out what is f of b minus f of a. So this would be capital F of 1 minus capital F of 0. All right, well, capital F of 1 would be equal to 1 cubed over 3, which is 1/3. Capital F of 0 would equal 0 cubed over 3, which is 0. 1/3 minus 0 is 1/3. So what we've computed is that the area underneath that curve is 1/3. Now, I'm writing out a lot of notation here that can really be simplified if we use that alternate notation that I just introduced on the previous slide. But what it would look like, the simplest way to condense everything that we've done so far would look like this. We have the definite integral 0 to 1 of x squared with respect to x is equal to, we would first of all compute an antiderivative, so x cubed over 3, or if you like 1/3 x cubed. You then draw this vertical bar. This notation just means I'm about to evaluate this at two different numbers. I'm going to plug in 1, then I'm going to plug in 0, and the implication here is that after you plug in 1 and 0, you would subtract them in that order. Okay, so this would be equal to 1/3 minus 0, which is just 1/3, like so. So the most common way and the shortest way to write out your notation does look like this. Now, even though we had answered these other two questions by computing areas of triangles, you could also, if you want, go in and think of what is an antiderivative of x, it would be x squared over 2, evaluate it at these two numbers, subtract them in that order, you'll find you get 1/2. Similar thing here, what's the antiderivative of x minus 2? Be x squared over 2 minus 2x. So if you list out capital F as x squared over 2 minus 2x, and then evaluate it at 2 and at 0, you'll find that you end up with -2 as your answer. From here, I just want to look at more examples. These will start with a function, definite integral 0 to 5 of 8x with respect to x. At the end of the problem, we will draw a picture that represents what the area would look like, but we can solve this from a purely analytical approach. So if you're trying to evaluate a definite integral, you first of all have to figure out an antiderivative of 8x. So any function whose derivative would give you 8x, I'm going to choose 4x squared. You're technically allowed to pick any value for plus c that you would like. I'm picking 0. Once you've identified the antiderivative, you draw your notation that says I'm about to plug in two different numbers, indicate what these two numbers are, and then go ahead and evaluate this. Using a calculator if necessary, probably this first one won't be necessary. If we plug 5 into the function, 5 squared is 25. 25 times 4 is 100. Then you put 0 into the function. 0 squared is 0. 4 times 0 is 0. So it'll be 100 minus 0, and we end up with 100 as our answer. Now that we have our answer, we can think about what would the graph of this look like. So if you think about the graph of y is equal to 8x, it goes through the origin. It also goes through, like if x is 10, our y value would be 80, so it goes through that point there, continues in both directions forever. And we are looking at how much area was under that curve, that line from 0 to 5. So 0's here, 5 would be halfway through. So we'll put in 5 right here. And the area, I know that the scale is very large, so it doesn't really look like this is 100 square units, but it is. From 0 to 5, on this line, you would have a total shaded area of 100 units underneath the line. Okay, let's go ahead and do another example. So for this next one, I want to look at the definite integral 1 to 4 of 10 minus 4x with respect to x. Here we observe that f is comprised of two different terms, so when you compute its antiderivative, first think about the antiderivative of 10, then the antiderivative of negative 4x. Okay, so that would be 10x is a function that would give me 10 as its derivative, minus 2x squared is a function where if I took this derivative, I would get the 4x. So we've found an antiderivative. We want to evaluate this antiderivative at 4 and at 1, and then subtract the results. So this will be, here it might be helpful to have a calculator. We're going to put 4 into the first part, that would give me 40. When you put 4 into the next part, you get 4 squared is 16, 16 times 2 is 32, 40 minus 32 is 8. So plugging 4 in, all of it together ends up giving you 8. Then you're going to subtract what you get when you plug in 1. So what do we get when we plug in 1? If you plug in 1, you get 10, minus plug in 1, you get 2. So it'd be 10 minus 2, which is also 8. And we end up with 0 as our answer. And that's kind of interesting. You might want to stop and think, what just happened? Like, how is it possible for the area under a curve to be 0? Well, let's look at what this would look like. A graph of this function, let's see, the original function has a y-intercept of 10 and a slope of negative 4. So we can draw this here. So 10 and a slope of negative 4 means that this line is going to cross the x-axis halfway between 2 and 3. And then we do go all the way to 4. The line continues forever, but we only looked at the area between 1 and 4. So you have this area on the left, you also have this area on the right. Now my diagram doesn't really do it justice because I'm just kind of freewheeling this. But these two areas should look like they're the same. We have part of the area under the curve is actually above the x-axis. So when your area is above the x-axis, when the curve is above the x-axis, then you have a positive 8. And then when you have an area that's underneath the x-axis, because the line was underneath the x-axis, then this would be a negative area. So what's going on behind the scenes here is that this was a positive 8, this was a negative 8. So then when we combine these two together, we ended up with 0. We can look at more examples. So definite integral, let's go 0 to 5 of e to the 7x. Let's see what this has to be with respect to something. So I'll say with respect to x. So for this, you would first of all compute an antiderivative of e to the 7x. That's just e to the 7x over 7. Right, this is a function where if we took its derivative, we get back to this. We're going to evaluate this at 5 and then at 0. Now this is something that you could technically put in your calculator, e to the 35 over 7, e to the 35 over 7, And then when we plug in 0, you get e to the 0 over 7, but e to the 0, any number to the 0 is just 1, so it'll be 1 over 7 when you plug in 0. And yes, you can put this in your calculator, but it's going to give you a really obnoxiously large number. So this is the exact answer. If you have some reason that you would want to round it to the nearest whatever, you can plug that in. But again, it's going to be so large that the calculator doesn't even show all of the decimal places. Now, in a brief calculus class, we aren't going to get too much into like these definite integrals. We really just look at a couple basic examples here at the end of the semester. But there are some properties of integrals that just are always true, and I want to present one of these to you. So if you're ever looking at a integral that has a lower limit and an upper limit that are the same, then even if you don't know what this function is, or even if you know it and you can't compute its antiderivative, you can always tell me what what this definite integral is equal to. So for example, let me pick a function where we don't know the antiderivative, e to the x squared. So you look at this and you're like, okay, this is a function and I can't compute its antiderivative. Now, if you feel like you can, go ahead and write the function that you think is this antiderivative, but when you compute the derivative of this function, it won't be this. This is a kind of a classic example of a function that's fairly simple that just doesn't have a nice, like, written out antiderivative. But even still, even though we don't know what the function would be, the capital F function, if the lower limit and upper limit of integration are the same, then we know what this answer is. The answer's got to be 0. Well, let me walk you through two ways to think about this. Well, first of all, this is a continuous function, so its antiderivative will exist. This is continuous for all x values, so its antiderivative will exist for any values, including the one that we picked. So even though we can't compute what capital F is, we know it exists, and if you plug in two numbers to it that are the same number, then you would be looking at f of 6 minus f of 6, and any value minus itself is going to give you 0. So that would be maybe the primary way to think about this. If you want a visual for like what's going on with that explanation, e to the x squared is going to look reminiscent of this, just the regular exponential function, but it's going to increase more rapidly than usual. And at some point over here, there's the value 6. Well, if I ask you how much area is underneath the curve from 6 to 6, well, because I picked the same number as the beginning and the end point, the width of that would be 0, so there is no area under the curve if you give yourself a width of 0. So that would be like the visual, or yeah, the visual explanation for why this answer would be what it is. All right, that is the only property of integrals that I want to specifically talk about. If you are curious and you want to study a little more, you can do a quick Google search for properties of integrals, and you'll see a lot more of like ways that like things that we know about integrals, even if we don't necessarily know too much about the function. The last example I would like to look at in this video is a word problem. So suppose that we have a store that has a sales revenue that's changing at a given rate. So S is going to be the sales, S prime is the rate of change of sales, and this is given to us in dollars per day. So T is going to be the number of days after an advertising campaign ends, so we're going to examine it. Really, the model is only going to be good for the first 30 days after the campaign ends. What we're going to look at specifically, though, is the first week and then the second week. So we want to find the total sales for the first week after the campaign ends. Well, we don't have total sales. We have the rate of change of the sales function. Well, we can compute this by constructing a definite integral. they told us to look between times equal to 0 and 7. So we're just looking from the initial day to the 7th day. And the function that we are examining is negative 30t squared plus 340t. This is, since it's a definite integral, we need to be integrating with respect to t. Just whatever the variable is here is the one that we're going to be using here. And when we're evaluating this, you would need to compute an antiderivative of this function. So antiderivative of negative 30t squared should be negative 10t cubed. We get that, of course, by increasing the exponent by 1 and then dividing by the new exponent. So when you increase this to 3 and then divide by 3, 30 divided by 3 is how we're getting this negative 10. When we do a similar thing for integrating or finding an antiderivative of 340t, we increase the exponent, divide by 2, so then 340 divided by 2 would give us 170. And we don't include the plus c, of course, and we're going to evaluate this at two numbers, at 7 and at 0. All right, if you pull out a calculator and plug 7 into, sorry, not that function, into this function, then you would get 4,900. When you put 0 into that function, you would get 0. So what do we have? We have 4,900 minus 0 is just 4,900. All right, so what does this mean? The total amount of sales that accrued during those 7 days would be equal to $4,900. If, though, you didn't want to look at the first week, what if we only wanted to look at the second week? Then you would have to start at the 7th day and go up to the 14th day. So our process is going to be the same. The only thing that's going to change is the limits of integration. So we still have the same function dt. It still has the same antiderivative, negative 10t cubed plus 170 t squared. This time the limits of integration are 14 and 7. Now when you plug in 14, we get 5,880. When we plug in 7, we still get the 4,900. So when you subtract these two, you should see that you have $980. Right, if this is our business, like, we can verify that we got most of the benefit from this advertising campaign in the first week. In the second week, this decrease, it's almost 1/5 of the productivity is what we currently had. This, of course, lasts for the entire month, so you can imagine that as we continue, it's likely that we will see this continued decrease in the effectiveness of the advertising campaign. All right, that finishes out this video. Hopefully you find it helpful as you're thinking about definite integrals and the fundamental theorem of calculus.